Welcome to our deep dive into advanced Java topics. We are starting with the foundational elements of any Java developer's toolkit, the development tools. Integrated development environments or IDEs are crucial for writing, debugging, and running Java code efficiently. Popular choices you will encounter include Eclipse, IntelliJ IDEA, and NetBeans, each offering a rich set of features like intelligent code completion that predicts and suggests code, powerful refactoring tools to restructure your code safely, and integrated debuggers for pinpointing and fixing issues. These features significantly boost your productivity and streamline the coding process. Beyond the IDE, building tools like Maven and Gradle are indispensable. They automate the entire process of compiling source code, managing project dependencies by downloading necessary libraries, running automated tests to ensure correctness, and packaging applications into deployable artifacts. This automation makes complex projects manageable, repeatable, and less prone to manual errors. And of course, no modern development workflow is complete without robust version control. Git stands as the industry standard, allowing developers to track every change to their code base, collaborate seamlessly on shared projects, and revert to previous states of their code if needed. Mastering these tools is the first essential step towards becoming a proficient Java developer, laying the groundwork for all the advanced concepts we will explore. They ensure your development environment is robust, your builds you are consistent, and your code is safely managed within a team setting, crucial for any serious Java project's success. Moving on to Java packages, a fundamental concept for organizing your code and avoiding naming conflicts. Think of packages as hierarchical folders that group related classes and interfaces together, creating a structured and manageable code base. This systematic organization is vital, especially in large scale applications where numerous classes developed by different teams or from various libraries must inadvertently have similar names. Packages effectively prevent naming collisions by providing unique namespaces, ensuring that my class in com.example.app is distinct from my class in org.another project. Java itself comes with a suite of built-in packages that are essential for everyday programming tasks. For instance, java.lang contains fundamental classes like string for text manipulations and text system for standard input-output operations. These are so vital they are automatically imported into every Java program. The java.util package provides a rich collection of utility classes for data structures like array list and hash map, along with classes for data and time operations. Meanwhile, java.io is crucial for input and output operations, handling file systems and streams for data persistence. Understanding how to utilize existing packages effectively and create your own well structured packages is key to writing clean, maintainable, and scalable Java applications. They promote better modularity, making navigation through complex projects easier, and significantly improve code reusability across different parts of an application or even separate projects. Next up, we have Java annotations, a powerful feature introduced to provide metadata to Java code without altering its execution logic. Annotations essentially embed supplementary information directly into your source code, which can then be processed by compilers for checks, by development tools for code generation or analysis, or by runtime frameworks for configuration or behavior modification. You have likely come across common annotations such as at the rate of override, which explicitly indicates that a method is intended to override a method in a superclass or implement an interface method, helping the compiler catch common errors like method signature mismatches. At the rate of deprecated signals that a program element like a class, method, or field is no longer recommended for use, guiding developers towards newer, more appropriate alternatives and indicating potential future removal. and at the rate of suppress warnings is used to suppress specific compiler warnings for particular code sections, allowing developers to manage compiler feedback more precisely and focus on critical issues. What's even more flexible is the ability to create custom annotations. This allows developers to define their own specialized metadata, which can be incredibly useful for building custom frameworks, performing compile time checks for adherence to coding standards, or even generating boilerplate code automatically. Annotations are a concise and elegant way to enrich your code with additional context, enabling sophisticated tooling, advanced code analysis, and highly configurable application behaviors. Now let's talk about a game changer introduced in Java 8, Lambda Expressions. These concise blocks of code enable functional programming paradigms in Java, bringing a new level of expressiveness and readability to your code. Before Lambdas, implementing single method interfaces, often referred to as functional interfaces, required writing verbose anonymous inner classes, which could make the code unnecessarily long and difficult to read, especially for simple operations. Lambda expressions streamline this by allowing you to treat functionality as a method argument or to declare an instance of a functional interface directly, effectively making code significantly more compact and focused on the core logic. The syntax is remarkable, simple, and intuitive for single line operations or for multi-line logic. This compact syntax makes your code much cleaner, especially when dealing with the collections and callbacks. For instance, sorting a list with a custom comparator, processing elements in a stream, or handling events becomes significantly more elegant and less cluttered, focusing on what rather than the how. Lambdas encourage a more declarative style of programming, where you express the desired outcome rather than the step-by-step procedure. They are a cornerstone of modern Java development, paving the way for more functional patterns and dramatically improving code conciseness, readability, and overall maintainability. Building directly on the foundations laid by Java 8, we have the powerful Java Streams API. This API provides a high-level declarative way to process collection of objects, offering a more functional and expressive approach to data manipulation compared to traditional iterative for loops. Streams allow you to perform a sequence of operations on data, forming a pipeline that can be incredibly powerful. You can filter elements based on specific conditions, example finding all numbers greater than 10. Map elements to a new form, example transforming a list of person objects into a list of their names, or reduce them to a single summary result like summing all numbers in a list or finding the maximum value. What makes streams particularly effective is their ability to process data efficiently. They can often leverage multi-core processors for parallel execution of operations, although this parallelization is largely handled implicitly by the API, simplifying concurrent programming. They promote a pipeline-like approach where data flows through a series of intermediate operations, which are lazy and don't process data until a terminal operation is called, and in a single terminal operation, making complex data transformations more readable and less prone to errors compared to nested loops. The Streams API significantly enhances the expressiveness and conciseness of Java code when dealing with data processing, making it an indispensable tool for modern data-intensive applications and a key component for writing efficient and elegant Java code. Let's delve into a crucial behind the scene aspect of Java, memory management. One of the Java's significant advantages over languages like C++ is its automatic garbage collection, which largely frees developers from the tedious and error-prone task of manually allocating and deallocating memory. This greatly reduces memory leaks and improves application stability. However, understanding how Java manages memory is still vital for writing efficient and performant applications. And for diagnosing memory related issues, Java divides memory into two primary areas, the stack and the heap. The stack is a LIFO, last in first out structure used for storing local variables, primitive data types, and method call frames. Memory allocation and deallocation here are extremely fast and automatically managed. The heap, on the other hand, is where all the objects created by new keyword are stored, and it's managed by the garbage vector which reclaims memory occupied by objects that are no longer referenced. Understanding the distinction between these two is important for optimizing memory usage and preventing issues like stack overflow error when the stack runs out of space or excessive garbage collection, which can impact performance. Furthermore, Java introduces different types of references beyond the standard strong reference, weak and soft references. These special references offer more fine-grained control over how objects are garbage collected, allowing for more flexible memory management strategies, particularly in caching memories mechanisms where you might want objects to be collected when memory is low. A solid grasp of Java's memory model is essential for diagnosing performance issues, avoiding memory-related bugs, and writing robust, high-performing applications. Now let's explore Java networking, which enables Java applications to communicate over networks. The core functionality for network programming in Java is provided by the java.net package. This package offers a comprehensive set of classes for building network applications, supporting both the reliable connection-oriented transmission control protocol or TCP and the faster connectionless user datagram protocol or UDP. Key classes within this package include socket and server socket for establishing and managing TCP connections, allowing client-server communication. The URL class simplifies working with uniform resource locators, making it easy to access resources on the web. For more advanced web interactions, HTTP URL connection provides capabilities for making HTTP requests and handling responses. Whether you are building a simple client-server application, fetching data from a web service, or developing a more complex distributed system, the Java Networking API provides the necessary building blocks to handle various network communication needs efficiently and securely. Moving on to Java Database Connectivity or JDBC, a standard Java API that allows Java applications to interact with relational databases. JDBC acts as a bridge, providing a consistent way for Java programs to connect to a wide variety of databases, regardless of the underlying database vendor. It enables developers to execute SQL statements directly from their Java code and retrieve the results. The API provides classes and interfaces for establishing a connection to a database, sending SQL queries, updating records, and processing the written datasets. This means you can perform operations like selecting data, inserting new rows, updating existing ones, and deleting records all within your Java application. JDBC is a fundamental component for any Java application that needs to store or retrieve data from a relational database. From simple desktop applications to complex enterprise systems, it provides the necessary abstraction to work with databases efficiently and reliably, making it a cornerstone for data-driven Java applications. Security is a paramount in today's interconnected world, and Java provides a robust framework for it through the Java Security API. This comprehensive API offers functionalities covering various aspects of application security, including cryptography, secure communication, and authentication mechanisms. The core packages for security are java.security and Java X.crypto. The Java.security package provides fundamental classes and interface for Java X.crypto package extends this with the classes for encryption and decryption, key generation, and message authentication codes. With these tools, developers can implement secure data storage, ensure the integrity and confidentiality of transmitted information, and verify the identity of users and applications. From secure coding practices to implementing complex cryptographic algorithms, the Java Security API offers the necessary tools to build secure and trustworthy applications that protect sensitive data and operation against various threats. Starting with Java 9, the platform introduced a significant architectural change, Java Modules, also known as the Java Platform Module System or JPMS. This feature enables modular programming, allowing developers to define explicit boundaries for their application components. At the heart of the system is the module info.java file, which is used to define a module. This file declares the module's name, its dependencies on other modules, and the package it exports to other modules. The primary goal of modularity is to improve application structure and scalability by making dependencies explicit and enforcing strong encapsulation. This means that components only expose what they intend to, preventing accidental misuse of internal APIs. Modularization also helps reduce the size of Java runtimes by allowing applications to include only the necessary modules, leading to smaller deployment footprints and faster startup times. For large and complex applications, Java modules are instrumental in managing complexity, improving maintainability, and fostering better long-term scalability. Let's discuss the Java Collections Framework, a cornerstone of data handling in Java. This framework provides a unified architecture for representing and manipulating collections of objects, offering a wide range of interfaces and classes to handle various data structures. Key interfaces you will frequently use include list, which maintains ordered sequence of elements and allows duplicates, set, which store unique elements with no specific order, queue, which typically order elements in a FIFO, first in first out manner, and map, which stores key value pairs. Alongside these interfaces, the framework provides concrete implementations like array list for dynamic arrays, hash set for efficient set operations, and hash map for fast key value lookups. The collection framework allows developers to choose the most appropriate data structure for their specific needs, enabling flexible and efficient data manipulation. It's an indispensable part of Java, simplifying tasks like storing, retrieving, and manipulating groups of objects, making your code more robust and performant. Let's explore the Java Reflection API, a powerful and advanced feature that allows Java programs to inspect and modify their own structure, behavior, and fields at runtime. This means a Java application can examine classes, interfaces, fields, and methods at runtime, and even create new instance of objects, invoke methods, and get or set field values dynamically. The core components of this functionality reside in the java.language.reflect package. While Reflection offers incredible flexibility and dynamic capabilities, it should be used judiciously, and it can incur performance overhead and potentially break encapsulation, making code harder to maintain. However, it's a cornerstone for many advanced Java frameworks such as Spring, which heavily relies on reflection for dependency injection, aspect-oriented programming, and various configuration capabilities. Understanding reflection is key to comprehending how many powerful Java libraries and frameworks operate, enabling you to build highly configurable and adaptable applications. Now we come to Java multi-threading, a critical concept for building responsive and efficient applications that can perform multiple tasks concurrently. Multi-threading enables the execution of different parts of a program, known as threads, simultaneously or seemingly simultaneously. This is particularly useful for applications that need to handle user input, perform background computations, and communicate over a network all at once without freezing the user interface. Java provides robust support for multi-threading through classes like thread and runnable, and more advanced constructs like executors for managing thread pools. Key methods include start to begin thread execution, run, which contains the code executed by the thread, and join to wait for a thread to complete its execution. While multi-threading offers significant performance benefits, it also introduces challenges like thread synchronization and managing shared resources to prevent data corruption. Mastering multi-threading is essential for developing high-performance and scalable Java applications. Let's discuss Java design patterns, which are essentially proven solutions to common software design problems that arise repeatedly in various contexts. They aren't concrete implementation, but rather blueprints that can be adapted to solve a particular design challenge in a specific situation. Design patterns encourage reusable and scalable code by providing a common vocabulary and understanding among developers. Examples include the singleton pattern, which ensures a class has only one instance and provides a global point of access to it. The factory pattern provides an interface for creating objects in a superclass, but allows subclasses to alter the type of objects that will be created. And the observer pattern defines a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. Understanding and applying design patterns is crucial for writing robust, maintainable, and extensible Java applications, enabling you to build systems that are flexible and adaptable to changing requirements. Next up is Java File I/O, which is fundamental for any application that needs to interact with the file system. Java provides comprehensive capabilities for reading from and writing to files through its java.io and java.nio packages. The java.io package contains traditional classes like file reader and buffer reader for character based input and file writer and buffer writer for character based output, making it easy to process text files line by line. For binary data, file input stream and file output stream are used. More recently, the new IO or NIO package was introduced, offering enhanced performance and features, especially for large-scale data operations. NIO provides channels and buffers for more efficient data transfer and supports non-blocking IO, which can be advantageous in higher performance network applications. Whether you are saving application data, processing configuration files, or handling large data sets, a solid understanding of Java's file IO mechanism is essential for building robust and reliable applications. Let's shift our focus to building graphical user interfaces or GUIs with the Java Swing. Swing is a GUI toolkit that provides a rich set of components for creating desktop applications with a look and feel that can be customized across different operating systems. All the core Swing components are found within the Java X.Swing package. You will find common elements like JFrame for the main application window, JButton for clickable buttons, and JLabel for displaying text or images. Swing applications are typically event driven, meaning they respond to user actions like button clicks, mouse movements, or keyboard input. This involves attaching event listeners to components that execute specific code when an event occurs. While modern Java development for enterprise often leans towards web-based interfaces, Swing remains a viable option for standalone desktop applications, offering a powerful and flexible way to create interactive user experiences directly on the user's machine. Understanding Swing provides valuable insights into event-driven programming and GUI design principles. Moving on to Java serialization, a powerful mechanism that allows you to convert Java objects into a byte stream. This byte stream can then be stored in a file, transmitted across a network, or stored in a database. And later, the byte stream can be deserialized back into a living Java object to make an object serializable. It class simply needs to implement the serializable interface, which is a marker interface that doesn't require any methods to be implemented. Serialization is incredibly useful in various scenarios. For instance, it's widely used in caching systems to store and retrieve complex objects quickly, in messaging queues for transmitting objects between different processes or applications, and in remote method invocation (RMI) to pass objects across network boundaries. It provides a convenient way to persist the state of objects and exchange them between different Java applications, enabling robust communication and data persistent solutions. Let's talk about Java internalization, often abbreviated as I18N due to the 18 letters between I and N. This capability is crucial for developing global applications that can be easily adapted to different languages, regions, and cultural conventions without requiring significant code changes. Java provides excellent support for internalization through classes like java.util.local and resource bundle. The local class represents a specific geographical, political, or cultural region, allowing you to define language, country, and variant preferences. Resource bundle are used to store local specific objects, typically strings, images, or sounds, allowing you to separate localized content from your code. This makes it incredibly easy to switch the application's language and region dynamically, providing a tailored experience to users around the world. Implementing I18N ensures that your software can reach a wider audience and cater to diverse linguistic and cultural requirements, making it a vital aspect of modern application development. Finally, let's wrap up with some essential Java best practices, which are guidelines that help you write high quality, maintainable, and efficient code. First and foremost, always use meaningful variable names. Descriptive name makes your code self-documenting and much easier for others and your future self to understand, reducing the need for excessive comments. Secondly, consistently follow coding standards, whether it's Oracle's conventions or your team specific guidelines, adhering to a consistent style improves readability and uniformity across a project. Thirdly, handle exceptions properly. Don't just catch and ignore them. Log errors, provide informative messages, and recover gracefully when possible. This prevents unexpected application crashes and aids in debugging. Lastly and critically, write unit tests. Unit tests verify the correctness of individual components of your code, catch bugs early, and provide a safety net for refactoring and new feature development. Adopting these best practices will significantly improve the quality, reliability, and maintainability of your Java applications, leading to more robust and scalable software.